Start streaming. Click. Where's the record button? Record. There we go. Yeah. Okay, cool. So let's pick up where we left off. Let's go to writing mode. Okay. God, everything is so difficult to do. Microsoft OneNote. There we go. Let's use this one. Let's turn that one off. Oh, there we go. Yeah. Okay. Oh, perfect. Okay. So we left off with functions of several variables. So I guess the thing we should talk about is just remind ourselves all of these things because it's been a while. So if you remember vector valued functions, they have a single input. Let me turn on my Wacom so I can highlight stuff. Oh, there we go. So you have a single input and you have multiple outputs. Okay, so that means that your input is a scalar, it's one number, and then you get like a several component vector out of it. Now the thing that we're going to be dealing with now is functions of several variables. It's the other way around. Instead of a single number being inputted, you have multiple numbers being inputted. And then what's being outputted? A single number, a scalar. So the way you can sort of think about it is that you're now inputting vectors and outputting scalars. Before, you were inputting a scalar and outputting a vector. It's completely switched now. Now, we don't think of ourselves as inputting a vector, though. We think of ourselves as, what's the word? Taking like a point on the plane or a point in space. Okay? So like I have this like picture here. So for a function of two variables, you can see in the little like blue looking blob, you have a bunch of points right there, right? Those points have x and y values. So your inputs are those individual points. They come with an x value and a y value. Then what happens? You take that x and that y value, you put it into your function f, and then it spits out a single z value, right? And the single z value is now on the real number line. Okay. Now, what happens in practice, though, is that you get graphs that look like this, however. Okay, so what you do is you take a point on the xy plane. Right, so like I'm gonna just use myself as an example. Let's say you have, let's use this book. Oh no, let's use the Wacom tablet. The Wacom tablet is my xy plane. You choose a point in the xy plane, you put it into the function, and then the function determines how high up the point should go. Okay, so like a point right here might give you something this high. A point right here might give you something that high. And that gives you a surface. Okay, so what you end up dealing with are surfaces usually. Okay, and we're gonna like investigate that more today about how all of this works in terms of the graphs. Okay, so I'm going to open up a Mathematica. Actually, no, I'm not going to open up a Mathematica. We're going to move on to the next section to talk about this, to explain it. Okay, so let me open up Add Page. We're going to talk about limits and continuity. Paper style, 300% zoom. Okay, there we go. Okay, so I want to remind you, first of all, about limits, the way we learned about them in 101A. So let's draw a little picture here. I'm going to put in an x and a y axis. Okay, let's put in our function f of x. Okay, now when you do limits, you talk about the limit as x approaches a of f of x equals L. I hear cop sirens. Woo woo. There we go. Okay, so we have our point. Let's say our point is right here. Okay, that's where x is equal to a. Okay, and that's why you have this value right here, right? X is going to a. Okay, now where do I draw L? If x is approaching a, then where does the L belong? It's a what? It's on the y-axis. Yes, so the x, A is an x value, L is a y value. Together they form a point in the xy plane. So let's put that over here. Okay, so there's L. Very good. So L is a y value. A is an x value. Now, you may not have covered this in your 101A class, but we say that who here, do we remember the epsilon delta definition for for a limit? Who here talked about the delta epsilon statement of a limit? Let's find out. Who here talked about the delta epsilon? Say yes or no in the chat. Did you or did you not talk about that in 101A? Okay, cool. So let's just remind everyone a little. Okay, so what does it mean for the limit of f of x as x approaches a to be equal to L? Well, what that means is that if for every epsilon greater than 0, there exists delta greater than 0 such that if the distance between x minus a is less than delta, then the distance between f of x minus L is less than epsilon. Okay, so let's talk about like what the fuck that means. Okay, this is what it's telling you. This part right here, it's saying this point A, which is right here, and your point X. So let's give these two things. There we go. So if this is your A and this is your X, how far away can they be at most? So what's the distance between them at most? It's greater than 0, but it's at most how much? Okay, so let's talk about how this works. Okay. When you look at absolute value and subtracting between two things, this is telling you that let's just say that the absolute value of a minus b equals c. What that means is that the distance between a and b is c. Okay, so you have two things being subtracted inside an absolute value. If you take the absolute value of two things being subtracted, that tells you how far apart those two things are. So if you look at back over here, you have x minus a. That means, and you're taking the absolute value, that means you're going to figure out how far apart x and a are from each other. Now, instead of saying equal, it's a less than. So we're saying the distance between x and a is less than what? Delta. So that's how you can interpret this statement. The distance between x and a is less than delta. So if we're talking about on a number line, here's a right here. And let's say delta is that far and delta is that far. That means x is some point between there. All right, so do you see how x is like nicely in that little region? Okay. So if your x is close enough to a, this is telling you that f of x, the distance between f of x and L will be less than epsilon. So if L is up here, you can go a distance epsilon that way, and you can go a distance epsilon that way. And what we now know is that f of x, which ends up right there, and ends up on the y-axis right here, there's f of x. Okay, so what this is saying is that here's, I wish I had like a highlighter. Here's f of x, here's x right here, and here's a. Do you see how x and a are very close to each other? If x is close enough to a, then f of x will also be very close to L. That's what it means for a limit to exist. It's telling you that as your x value gets closer to your a value, the f of x value would get closer to whatever your limit is equal to. So let's write this down. As x approaches a, well, so what does a limit mean? What does a limit mean? It means that as x approaches a, then f of x approaches the value of the limit. So let's look at an example where this breaks. Okay, like what's the sort of behavior that would make a limit not exist? Like, how should I draw a function so that the limit as, let's just say I want the limit as x approaches 3 of f of x to not exist. What can I draw to make this true? Like, what would I have to draw in my function? Oh, shit. I pulled out my cord. I can't hear anyone. 1 second. Okay, there we go. Okay, so like, scroll up. Say that again. I could have an asymptote, you're saying? Sure, so let's keep a list here. So if I want the limit to not exist, I can have an asymptote at x equals 3. What else could I also do to make sure that the limit doesn't exist? Okay, so I could have the approach different values from two sides. What else could I do? So like here, let's just do this one. Okay, so what I could do with the function, so here's x equals 3 right here. I could have my function do something like this. Let's say 1, 2, 3. My function could do this from the left, and my function could do that from the right. Okay, so in this case, the limit as x approaches 3 does not exist. Okay, now let's talk about why. Let's make that look a little nicer. Okay. So I'm going to choose a point right here. Yeah, I'm going to choose a point right there. So approximately, okay, let's look at this point. So let's say that you thought that the limit as x approaches 3 of this function was equal to 1. So does it make sense that you thought that that's what the limit was equal to because you look at this point right here and you notice that f of 3 is equal to 1? So you're like, maybe the limit is equal to 1. Okay, making sense so far? Like you can see in the picture, like, oh, if you plug 3 into your function, you get 1 because you have that closed dot on the bottom. I did not choose 3 because this is an open circle up here at the top. Does that make sense to everyone? Cool. Can we like read the drawing? Just want to make sure. Okay, cool. Now, if the limit was equal to 1, then what should I be able to do? Let's write that down. Okay, it's not letting me. If the limit is equal to 1, then I should be able to find a point close to x equals 3 such that, let's call that point, let's call it a b. So b is some number close to 3 such that f of b is close to 1. Okay, so what that means, so this point right here, this little blue point, that's my b. Does everyone see how that point b, let's put it down to the x-axis. Do you see how on the x-axis that point is pretty close to 3? Okay, wait, let's make it look straighter. There we go. Okay, there's my b. My b is rather close to 3. Okay, now, unfortunately though, what is f of b pretty close to? Or what approximately what is the y value f of b close to? So b is close to x equals 3, but what is f of b, the y value, close to? So b itself as an x value is pretty close to 3, but f of b, the y value, what is that close to? Yeah, so it's close to the y value of 3, right? Okay. Now, what was it supposed to be close to if the limit existed? 1, right? Now, here's the sad thing. If you look at this part of the graph up here, if you look at any of these points that are close to 3, do any of them have y values that are close to 1? No. And that's why the limit doesn't exist. However, if you look at the right side of the graph, let's say you choose a point like right here, that has a x value close to 3. And if you look at that point, what is the y value close to? 1, right? So does it make sense on the right, the limit is equal to 1, because if you look at the x values close to 3, their y values end up being close to 1. However, that doesn't happen on the left side. All of the x values close to 3 do not have y values close to 1. Okay, so hopefully this reminds you of how this works. Guess what we're going to be doing now? So this is limits for like what we have normally dealt with, functions that have a scalar input and functions that have a scalar output, right? An x and a y value. Now we're going to look at limits for functions that have multiple inputs and a single output. In other words, we're going to look at the limits for functions of functions of several variables. Okay, so let's do this. Let's do this now for limits of functions of several variables. Alright. So there's a bit of terminology that we have to deal with here. So let me first draw or write what we had for previously, and then over here let's talk about functions of several variables. Okay, so for functions of one variable, just x and y, our limit, we had the limit as x approaches a, right? That was our x value. The limit of f of x equals L. Okay, and that worked if the distance between x and a was less than delta, then the distance between f of x and L was less than epsilon. Okay, now L, what the limit was equal to, was the output variable on the y-axis, and A, what the limit was approaching, that was right here, and that was your input variable on the x-axis. Okay, so notice that what you're approaching in the limit was from your domain, and then what the limit was equal to was from your range. Does everyone get what I'm saying there? Like, you have the limit as x goes to a. X is your domain. Okay, so that's on your x-axis. What was the limit of f of x as x approaches a equal to? L, so the limit was equal to something from your range. And that's on the y-axis. So life is going to be a little more complicated for a function that has the domain as R2 and the range as R. So if you're talking about the limit is now not just x goes to a. The limit is going to have to be something from R2, so your limit is going to be the limit as x comma y approaches a comma b. Y is my limit now for a point. Like, why do I have limit x comma y goes to a comma b? Just see if people are following me. Yes, thank you. The function, the domain is R2, so what your limit is having you go to has to be something from there, right? Which means it has to be from the domain, and the domain is a point. The domain is no longer the xy axis. The domain is the xy plane. Or sorry, the domain is no longer the x-axis. The domain is the xy plane. Which means that when we reformulate this limit statement, we're going to say if the distance between your point x comma y and your point a comma b is less than delta. Okay. So now you have the limit of f of x as x comma y approaches a comma b is going to be equal to what? What is my range in this case? Is it equal to a point is my question. Am I going to have this be equal to something like, am I going to have this equal to c comma d? Am I going to have that equal to another point? Yes, exactly, because the output is the range, and the range is just r. The range is not R2. Thank you for paying attention and listening. I am happy. So this is going to still be equal to L. Why? It's still equal to a scalar because the output is still a scalar in the range. And this is now not, so the range is no longer the y-axis. What is the range now? Yes, exactly. The range is the z-axis. Before the range was the y-axis, now the range is the z-axis. So in our limit statements, it is if the distance between x comma y and a comma b is less than delta, then the distance between f of x comma y and L is less than epsilon. And that is on the z-axis. Okay, so now what we have to do is we need to talk about what the hell this is right here. Okay, so what this is telling you is that the distance between the point xy and the point AB is less than delta. Okay, this thing here has a special name. It is called, or actually, let's just talk about like what all this is. So, like, we have a point x comma y, and we have another point a comma b. Now, I'm telling you how far away at most are those 2 points. So if you look at the distance between them, what's the biggest that distance can get? No. Those are the 2 points. So x and y is one of the points in blue. A comma b is the other point in green. I'm saying the distance between them needs to be less than what, apparently? Delta. Okay, so imagine you start with x comma y as your center. And you make a radius of delta. Let's use the circle draw function. Make life easier. Okay, perfect. Okay. So do you see how I have here a circle of radius delta centered at x comma y? AB has to be a point inside of there, right? Because what did we say about x comma y and a comma b? The distance between them has to be less than delta, which means a comma b needs to be a point in that circle. Or disk, or whatever the fuck you want to call it. Right? So AB can be any point inside of there. This has a special name. We call this the delta disk centered at x comma y. The delta disk centered at x comma y. And why am I talking about this? Well, because the delta disk centered at x comma y is a collection of points. It is all of the points a comma b such that the distance between x comma y and a comma b is less than delta. Do we recognize this notation? Here I'm saying, what is this disk? Well, it's a bunch of points. And all of those points satisfy this condition. They are the points such that the distance between them and x comma y is less than some value. So if you want to talk about all the points in this disk, you would write it this way. Okay, why do we need this? Well, because in the limit statement, I was just talking about that. I was saying, well, if the distance between xy and AB is less than delta, well, I need to know what I'm talking about now. Okay, so what we're saying is, look, you have a point right here, x comma y. And let's say I have a point close to x comma y. The point that's close to x comma y is called a comma b. And how close is that point? Well, it's no more than delta away. Okay, now there's another point. There's another part of the statement in the limit. It's saying, well, f of xy is close to L. Okay, so let's draw what's going on here. Okay, so you have this point, x comma y. And you're talking, oops, let's make that a little bigger. Okay, let's say you have this point, x comma y. And this point is on the xy plane. So here's my delta disk. Now let's say you have a point that's close to x comma y. In other words, that point is in the delta disk. Let's call that a comma b. Now, what does it mean for the limit of x comma y approaches a comma b of f of x y to be equal to L? Well, it means if you choose a point A comma... Oh, actually, wait, shit, I wrote this backwards. My bad. Sorry. I apologize. Let me write the limit statement first. You have the limit of f of xy as xy approaches a comma b. That's equal to L. Okay, so what is this telling you? So we are approaching a point a comma b. So let's put that point here on the xy axis. So there's my point a comma b. Now remember, this point is on the xy plane, so let's draw the delta disk around it. Okay, so the delta disk is all the points that are no further away than delta away from a comma b. So let's imagine a point right here, x comma y. So this x comma y is no more than delta away from a comma b. Now, if the limit is equal to L, this is telling you that if you were to evaluate f of AB, that's equal to L. So over on the z-axis, so here is my z-axis, f of AB is equal to L. Now, a limit, what it's telling you is that, well, if you're close to your point AB on the xy axis, in other words, this point x comma y, well, what do I now know about this point? So if I was to evaluate this point f of xy, what does the value of that point have to be close to? Okay, so because xy was close to AB, what do I want f of xy to be close to? Yes, exactly. And that's all that this means. The first part of the statement tells you, well, xy is close to AB. That's what absolute value of xy minus AB less than delta tells you. This is telling you that xy is close to AB. Now the other part of the limit statement tells you, well, if xy is close to AB, then f of xy should be close to L. And that's what it means for the limit to exist. In other words, if you look on the xy axis, you're approaching AB, so AB is going to be the center of my circle. The disk around AB is all of the points that are close to AB. So you're like, okay, let's choose a point in that disk. Xy is no more than a distance delta away from AB. Now, if the limit is equal to L, that means when I plug the point xy into my function, whatever I get as my z value better be close to L. Now, if you draw this, what that means is when you draw your function, you're going to get a surface, like maybe like this. And what you're finding out is that if you choose a point xy that's close to AB, then f of xy on the surface is going to end up being very close to the value f of AB L. So as everyone's going to sort of see that, like you have that blue point, which is close to the green point in the disk. If the function is continuous, then the blue point on the surface is going to be close to the green point on the surface. And in fact, if you keep on choosing points that are closer and closer to AB, when you plug them into the function, they're going to get closer and closer. Okay, hopefully this makes sense. This weird looking thing right here, the white thing, that is called the image of the delta disk. Let's write that again. I did that horribly. Image of the delta disk. Okay, so what that is we took all of the points in that disk and we plugged them into the function, and that's what we got, that like weird, it basically deformed the disk. Okay, that was a lot for one day. I think we're gonna end here, because like, first day back, I don't want to like destroy